Okay, so this is for the 5x5x5 cube programmers in the group, and what I've done here was to create a 20 move single slice term metric puzzle that I pulled from my algorithm list. One of the algorithms was 8 moves in length, and then the second one was 12 moves in length, and I just applied them in cascade, one after the other, to create this cube position shown here. Oops. Well, it's kind of scrolled up there. But what I do is I have every wing algorithm that will match a displaced wing to a middle edge up to depth 14 computed. And there's surprisingly a small number. You can see in this blue column here, there's 78 algorithms at depth 6, 132 at depth 7. And you can see there's 62,890,834 at depth 14. That's not too many. And this count also includes the reverse of the alg. For example, there's an alg that will create the position, and obviously there's a reverse algorithm that will restore that position. I only store the alg that creates the position to the disk file, but I allocate twice as much RAM, and I run every algorithm in reverse. I also check to see that the reversing algorithm doesn't do the same thing as the forward moving algorithm, which that's a very special case. And if that's the case, then it's not duplicated into the hash table. So you can see in this white right here, this white text, it's telling me which file it's reading. It shows the count of the unreversed algorithms inside this file. And then it does something kind of clever that I came up with. The idea is not to just read the algorithms into a RAM buffer, but also put what the cube would look like with the algorithm applied into the hash table. And so I can basically take a cube that has everything except for the wings solved correctly. And then as I apply the algorithms blindly and check the status of it, at the terminal node, I could also ping the hash table and see if that cube configuration is in the hash table. And if it is, it pulls the move sequence out of the hash table and applies it. And we'll solve the cube. So even though I only have the algorithms through depth 14, I should technically be able to solve any cube position from 28 moves away in one pass. That is applying these let's see, what is it? There's probably 70 million algorithms altogether if you add them all up from depth 6 to depth 14. So and it's still reading the file down here for depth 14. This is taking a while, because the other thing I do as I'm adding entries into the hash table, I'm creating basically 4 entries per algorithm. One is obviously the algorithm itself. The other is the algorithm reversed. Then I do the same thing with the corners ghosted out. And I'll tell you why. When we're trying to solve the wings, if we're following the course of a standard reduction type solve, the corners could be in any configuration. And I don't want to hard code one particular corner configuration to a wing algorithm that's going to be in the hash table. And the reason for that's pretty obvious. I mean, we don't care what the corners are. we still want to be able to find the position in the hash table, even though we have the algorithm and we apply it and it's going to gain some progress. It could technically have everything that we want in the hash table, but the corners could be different. So it won't see that as a solution. So it won't apply it. So I decided to ghost out all the corners and turn them black. And that basically multiplies the size of the hash table by like 88 million. Whatever the total number of corner arrangements there are on the 2x2 cube, by creating an entry with and without the corners as part of the solve, really was kind of like the little breakthrough light bulb moment. So this hash table, even there's only, say, 70 million algorithms in it, you really want to multiply that by 88 million, and that's the total configurations that this thing should be able to solve. And not only that, I can call the algorithms in cascade. After I go through pass 1 and apply the algorithm to see which one gives the most progress, I can now match every algorithm up against every algorithm. Literally, say 70 million squared, which, what, million times a million? That's what, a trillion? 70, yeah. So that would that would be like 4.9 quadrillion possibilities if I'm doing my math right. I'm not sure. I'm just talking off the cuff here. Okay, so it's still reading the depth 14 file down here. It's taking longer than I thought. Yeah, there's 31,445,417 unreversed algs. So there's 62,890,834, including reversing. And then you could double that number again once you have the algorithm and the reverse of the algorithm without the corners, with the corners being ghosted out. So it's stuffing them all in that hash table. And let's see, I have roughly 4 billion slots for this hash table, which can store solutions up to 15 turns away from the solve state. So that's what, 4 billion 20,889, and that's a quadruple prime number. This last digit that ends in 9, if it ended in 7, 3, or 1, all of those numbers would likewise be prime. This is a quadruple prime. And we're still reading this file here. Oh, there we go. And holy crap. It just solved it. It's solved. It is. Yeah. It solved that in like a second. Holy crap. Okay, so right here in green is the important thing. I had it print stuff out in green if it finds a solution within the hash table. So this particular edge algorithm in yellow, which looks curiously like the scramble algorithm. I would expect that to have been in reverse. Let's see, 1R plus 2F plus 1R minus. Yeah, this is the exact, in yellow letters here, this is the exact way I sent it to the scramble with the first 8-move algorithm. Matter of fact, holy crap again, this, in green, this is what it found in the hash table, right? And this is not reversed either. This is the forward version of the algorithm that I entered. So this solution, I have to double check that. This solution is also equal to its scramble. That's pretty cool. So obviously, it was a big anticlimax. I mean, it took probably 10 minutes to load the table and 1 second to solve it. So I'm guessing this will be a pretty powerful technique once I start getting to some random scrambles. Anyway, I'm going to sign off for now. Can't believe it took all that time to load it and then instantaneously solved it. And I'll post this online in a couple minutes for you guys to check out.